like the concept of the mole, balancing equations is one of those ideas that you learn in first year chemistry class that tends to give a lot of students a hard time, even though it is a fairly straightforward concept. I think what makes it difficult is that there's a bit of an art to it. So before we talk about balancing chemical equations, what is a chemical equation? Well, here's some examples right here, and I have some more in the rest of this video. But it essentially just describes a chemical reaction. You got some aluminum, you have some oxygen gas, or the diatomic oxygen molecule, and then you end up with aluminum oxide. And you would say, okay, fine, that's an equation. It looks nice. I have my reactants, or the things that react. These are the reactants. And then I have the products of this reaction. What's left there to do? Well, you have a problem here. The way I've written it right now, I have one atom of aluminum plus two atoms of oxygen, right? They're bonded to each other, but there's two atoms of oxygen here. One molecule of diatomic oxygen, or one molecule of oxygen, but they have two oxygen atoms here. And when you add them together, what am I? I have two atoms of aluminum and three atoms of oxygen. So I have a different number of aluminums on both sides of this equation. On this side I have one aluminum. On this side I have two aluminums. And then I have a different number of oxygens. On this side I have two oxygens. And on that side I have three oxygens. So balancing equations is all about fixing that problem. So I have the same number of aluminum on both sides of the equation and the same number of oxygens on both sides. So let's try to do that. I'll do it in orange. So I said, just what I said, I have one aluminum here and I have two aluminums there. So maybe a simple thing is just to put a 2 out here. So now I have two aluminums on this side and I have two aluminums on this side. The aluminums look happy. Now let's look at the oxygen. Here I have two oxygens on the left-hand side of the equation. And on the right-hand side of the equation, I have three oxygens. What can I do here? Well, if I could kind of have half atoms, I could just multiply this by 1.5. 1.5. 1.5 times 2 is 3. So now I have three oxygens on both sides of this equation, and I have two aluminums on both sides of the equation. Am I done? Well, no, you can't have half an atom or 1.5 of an atom. That's not cool. So what you do is you just multiply this so that you end up with whole numbers. So let's just multiply both sides of this whole equation by 2. And we have 4 aluminums plus 3 oxygens yields, we multiplied everything by 2. 2 molecules of aluminum oxide. Now, you might have been tempted at some point in this exercise to say, oh, well, why don't I just tweak part of the aluminum oxide? Why don't I put a 2/3 in front of this oxygen? You cannot do that. The equation is as it is. The molecule aluminum oxide is aluminum oxide. You can't change the relative ratios of the aluminum and the oxygen within the aluminum oxide molecule. You can just change the number of aluminum oxide molecules as a whole that you have, in this case 2. So what did we do? We looked at the aluminum. We said, okay, we need two aluminums to have both sides of that be 2. And then when we looked at oxygen, we said, well, if I multiply this by 1.5, then that becomes 3 oxygens here, because 1.5 times 2 oxygens, and 3 oxygens there. And then all we said is, oh, well, I can't have a 1.5 there, so let me multiply both sides by 2. And I ended up with 4 aluminums plus 3 oxygen molecules, or 6 oxygen atoms, yields 2 molecules of aluminum oxide. Let's see if we can do some more of these. So here I have methane, and that G in parentheses, I just wanted to expose you to that. That just means it's a gas. So I have methane gas plus oxygen gas yields carbon dioxide gas plus water, and that's an L there, so liquid water. So what can we do here? So the general thing is do the complicated molecules first, and then at the end you can worry about the single atom molecules, because those are very easy to play with. And the reason why you do that, whenever you change a number here, let's say we're trying to engineer how many carbons we have on both sides of this equation. If I set a number here, I'm also changing the number of hydrogens, and I'll have to play with the hydrogens there. And at the end, I'll have some number of oxygens, and then I have to tweak this number right there. So let's just start with the carbons. It seems complicated. When you go step by step and you kind of play with things a little bit, it should proceed fairly smoothly. So here I have 2 carbons. 2 carbons, and here I have, on the right hand side, I only have 1 carbon. So ideally I'd want 2 carbons on both sides of this equation, so let me put a 2 out here. So there you go, my carbons are happy. I now have 2 carbons and 2 carbons. Now let me move to the hydrogens. Remember, I wanted to do the oxygens last because I can just set this to whatever I want it to be without messing up any of the other atoms. So on this side of the equation, I have 4 hydrogen atoms. How many hydrogen atoms do I have on this side of the equation? Let's see. So I have 4 hydrogen atoms here. How many do I have on this side? Well, I have 2 hydrogen atoms right there. So I want to have 4 on both sides, so let me put a 2 in front of the water. So now I have 4 hydrogen atoms. Cool. Finally, oxygen. On the left-hand side, I have 2 oxygen atoms. And on the right-hand side, what do I have? I have 2 times this 1 oxygen right here. So right now that's 2, right? 2 waters. In each water I have 1 oxygen atom, but I have 2 oxygen. I have 2 water molecules, so I have 2 oxygens. And then I have, in the carbon dioxide, I have 2 oxygens in each carbon dioxide, and have 2 carbon dioxides, right? When I put that magenta 2 out front. So how many oxygens do I have? 2 times 2, I have 4 oxygens. So on the left-hand side, I have 2 oxygens. On the right-hand side, I have 6 oxygens. 2 in the 2 molecules of water, and 4 in the 2 molecules of carbon dioxide. So how do I make this 2 into 6? I want to have 6 oxygens on this side. I want to have 6 oxygens on the left-hand side as well. Well, if I put a 3 out here, now I have 6 oxygens. And my equation has been balanced. I have 2 carbons on this side, 2 carbons on that side, 4 hydrogens on this side, 4 hydrogens on this side, 6 oxygens on this side, and then 4 plus 2, 6 oxygens on that side. Next equation to balance. This actually becomes quite fun once you get the knack of it. So I have ethane. I have ethane plus oxygen gas yielding carbon dioxide and water. So this is a combustion process. So let's look at the carbons first. I have 2 carbons here. I have 1 carbon there. So let me put a 2 here. So now I have 2 carbons. Fair enough. And remember, I'm going to worry about the oxygen last. This one's actually not too different than the last problem. I have 6 hydrogens here. I only have 2 hydrogens in the water. So we only have 3 hydrogen molecules, 3 water molecules. And now I've balanced out the hydrogens. I have 6 hydrogens on both sides of the equation. And now let's deal with the water. Here, on the right-hand side, I have, I'll do it in this orange color. I have 2 oxygens in each carbon dioxide molecule, and I have 2 molecules. So I have 4 oxygens. And I have 1 oxygen in each water molecule, and I have 3 molecules, so I have 3 oxygens here. Is that right? 3 oxygens on the right-hand side. Yep, 3 water molecules. And then I have 4 oxygens in the carbon dioxide. Right. So I have 7 oxygens. I have 7 oxygens on this side, and I only have 2 on this side. So how can I make this 2 into 7? Well, I can multiply it by 3.5. Right? Remember, I just want to have 7 on both sides. If I have 3.5 of these diatomic oxygen molecules, 3.5 times 2 is 7. So now I have 7 oxygens on both sides of the equation. 4 plus 3, and then 7 here. 2 carbons, and then 6 hydrogens. And I'm almost done, except for the fact that you can't have fractions of molecules. So what you do is just multiply both sides of this equation by 2 or 3 or whatever you need to multiply it to get rid of the fraction. So if I multiply everything by 2, I end up with 2 molecules of ethane plus 7 molecules of diatomic oxygen, 7 O2s, yielding 2 molecules of carbon dioxide. Oh, sorry, I'm multiplying everything by 2. So 4 molecules of carbon dioxide. 4 molecules of carbon dioxide plus 6 molecules of water. And if you, just to make sure that that all still works, if you want to, you can check. How much carbon do we have? I have 4 carbons here. I have 4 carbons here. How much hydrogen do I have? I have 2 times 6. I have 12 hydrogens here. I have 12 hydrogens here. How much oxygen do I have? I have, let me do a different color. I have 14 oxygens here. And here I have 8 oxygens. And here I have 6 times 1. I have 6 oxygens. So 6 plus 8 is 14. So my equation has been balanced. So that one, a lot of people might have found that to be a hard problem because you have this 3.5, and just going straight to this might seem non-intuitive. But if you just work from the more complicated molecules and you go atom by atom, and if you end up with any fractions, you just multiply both sides by some number to get rid of the fraction, and then you're done. All right, let's do another one. So this one looks all hairy. I have this iron oxide plus sulfuric acid yields all this hairy stuff. But the key here to realize is that this group right here, this sulfate group stays together, right? You have this SO4 there, and you have this SO4 there. So to really simplify things for our head, you can kind of treat that like an atom. So let's make a substitution. We'll substitute that for X. And so if we rewrite this as, I'll do it in a vibrant color, iron oxide plus H2. There's only one sulfate group here, so H2, I'll do it in this X, and then that yields iron, 2 irons, this molecule with 2 irons, and it has 3 of these sulfate groups. 3 of these sulfate groups, and then plus water. All I did is replace the sulfate with an X, and now we can treat that X like an atom, and we can just balance the equation. So let's see. On the left-hand side, how many irons do we have? We have 2 irons here. We have 2 irons there. So the irons look balanced at first glance. Let's deal with the oxygens. So if we have 3 oxygens here, let me do it in a different color. We have 3 oxygens here, and we only have 1 oxygen here. And remember, there were some oxygens in this X group, but those the sulfate group stayed together, so we can just treat those separately. So if we want to have 3 oxygens on the right-hand side as well. So let's stick a 3 here. Whoops. Let's stick a. Sometimes my pen tool malfunctions. So let me put that 3 there. So now we have 3 oxygens as well. And then finally, let's see. Let's look at the hydrogens. So I have, or maybe I should. We have 3. Let's see, how many hydrogens do we have here? We have 6 hydrogens now on the right-hand side. 6 hydrogens here, 3 times 2. And we want to have 6 hydrogens here, so we have to have 3 of these molecules. And then finally, let's look at the sulfate group, that X. We have 3 X's here. And lucky for us, we have 3 X's over there. So our equation has been balanced, and if we want to write it back in terms of the sulfate terms, we can just unsubstitute the X, and we're left with iron, 1 molecule of iron oxide plus 3 molecules of sulfuric acid, H2SO4. I just unsubstitute the X with SO4, yields 1 of these molecules, SO4, 3. 4, 3. I just unsubstituted the X plus 3 molecules of water. Let's do one more, and then I think we'll be all balanced out. Carbon dioxide plus hydrogen gas yields methane plus water. So let's deal with the carbons first. I have 1 carbon here, 1 carbon there. The carbons look happy. Let's look at the oxygen. I have 2 oxygens here. I have 1 oxygen there. So I want 2 oxygens here, so let me stick a 2 there. And then let's deal with the hydrogens last, because this is the easiest one to play with, because it doesn't affect any of the other atoms. So if the hydrogen, I have 2 here, and I have 4 plus 4 here, right? I have 4 hydrogens there, and I have 4 hydrogens there. So I need 8 hydrogens on the left-hand side. So I just put a 4 there. And we're all done balancing. Anyway, hopefully you found that useful.